Bueno, pues nos reunimos hoy aquí para escuchar la charla que tiene que dar Juan López Cantalapiedra, que es un reciente miembro del Departamento de Paleontología y de Paleobiología. Y bueno, pues simplemente como una especie de recapitulación de su trayectoria y de sus trabajos, pues decir que ha estado involucrado con el museo desde casi al principio de su historia, en colaboración con la Universidad Complutense de Madrid, donde obtuvo su PhD, su doctorado. Ha colaborado en el sentido de que bueno, Jorge Morales era su co-supervisor de su tesis. Enseguida, después de haber acabado su tesis, tuvo varios contratos de postdoctorales, entre ellos pues, un Humboldt y una de la Fundación de Investigación Alemana. En su trayectoria ha visitado numerosos centros, tanto de Europa como de Estados Unidos y Canadá, con colaboradores de grandísimo renombre como Michael Fortelius en Helsinki y Anthony Bernowski en Berkeley, que han sido la base de la metodología que luego posteriormente ha refinado y ha perfeccionado en la aplicación de problemas más concretos en distintos aspectos de paleobiodiversidad, cuestiones de macroevolución y extinción. Viene además tiene una cualidad muy interesante, que es una gran capacidad de divulgación, tanto a nivel científico, con unas presentaciones que me parecen preciosas, pero también a nivel de divulgación social. Y bueno, pues ha liderado varias publicaciones en revistas de gran impacto, como son Nature, Science o Plus One, Evolution, y forma parte tanto de supervisión de tesis como de comisiones de evaluación nacionales extranjeras. Y sin más dilación, pues pasamos a escucharle y que va a ser seguramente muy atractivo e interesante.
Gracias. Buenos días English, right? Yeah. Good morning, everybody. Thanks for joining the seminar. So today I'm going to present something that results we're still digesting, so there won't be a lot of discussion because these are really recent results. But before I jump into the subject, I want to acknowledge that this is a huge collaborative work where we have people coming from different disciplines, from biomathematics to taxonomists to evolutionary paleobiologists. And there is a lot of work here, especially in specialists vetting the database on which all these analyses have been done, checking taxonomy, checking the dates of the records in our African fossil record, etc. And many of those here in this slide, they have a common interest because they study ungulates. And when we think about ungulates today, we can think of Africa as this true sanctuary for all these lineages. No? Africa is the place where we find the highest diversity in terms of species, the highest abundance of ungulates, and the highest biomass in the world in the shape of ungulate meat. And this is also true for megaherbivores, which we understand megaherbivores are species that weight above 1,000 kilos, so it's some boundary here. Because there is no other place in the world where we can see so many megaherbivores together from different lineages, not just proboscideans, but also like ruminants and things like this, rhinos, hippos, etc. So people have thought that we have so many large herbivores in Africa because Africa has for a longer time coexisted, these faunas have coexisted with hominids, and because of this, there was like a coevolution, so everybody was happy, and humans didn't harm these faunas too much, and this is why we have all these things in Africa today. So this is because people now thinking about how to restore original systems in terms of herbivore guilds have thought or are considering Africa as a baseline, as a reference for bringing back some of these processes in terms of biomass restoration and process restoration in ecosystems. But the truth is that even though when we see pictures like this, we think of Africa about this like pristine place in terms of diversity, the truth is that if we rewind a little bit back in time, we can see in the fossil record that our ancestors, for example, in this reconstruction of one site in Turkana, Kenya, around 3 million years ago, they were sharing the landscape with much larger density of megaherbivores. So it was very common. It's very common to go to Africa and in the same fossil site to find like several species of proboscideans, many of them going above 5,000 kilos, which is much larger than an African elephant. No? Only like super large African elephants that we know are maybe like 6,000 kilos, but this is super, super exceptional. So the question remains of, okay, so as we are compiling all this data, it's becoming evident that Africa is not this pristine refuge for large animals, but there was some decline in these faunas at some point in the past. And when we think about megaherbivore extinction, one of the first things that may come to our minds is the idea that humans would have caused their decline mainly through hunting, but also there is hypotheses talking about humans being able to disrupt food webs, so causing like extinction not just through direct hunting, but just through this disruption. And the idea is that it's always better to hunt larger things. It's energetically better than just hunt many impalas or kudus or dig-digs or whatever. So that this action would be size selective. So if we have an histogram of body sizes of mammals, terrestrial mammals in Africa, humans would have been trimming the histogram from the right side, from the larger categories. So you can see here like all the part that was lost, this white and gray parts of the bar. And we know that humans would have had these capabilities to hunt large things with projectiles and stuff like this, and they have enough population abundance maybe in the last 100,000 years more or less, right? So this could be like one scenario. But a few years ago, Tyler Faith and collaborators presented this study, and they were trying to put numbers and a timing on what this decline could have been. And they were looking at localities, fossil localities. Each of these points is a locality. And this is just residuals from a reference point, so 0 would be modern African systems. So you could see that starting around 4 million years, there is a decrease in the number of species we find in places, in localities. So there's a huge trend downwards, very clean trend downwards until we reach today's baseline. So this means that things were much richer in terms of local diversity of species. This is a species richness in localities. So this was like the first time we have some timing around this process. And later on, and inspired to some degree in this paper, last year, Faisal, Bibi, and I published this other paper where we are using a different data set. We are not even looking at the species richness because we are doing a taxon-free approach, and we are just looking at the relative abundance of sizes across all these ungulate faunas. So we don't care if they are proboscideans or rhinos or antelopes or whatever. And what we see is that both relative abundance by mass category here in different colors and relative biomass, they were decreasing very early in the larger categories, especially the abundance. So we did some statistics, and we have an inflection point around also like 3.6 million, so very close to these 4 million years that Faith et al. Had proposed. So this is also telling us there is some relocation of biomass, so you can see that the smaller categories, they are gaining in relative biomass in ecosystem. At the same time, these larger things are losing this presence. So this makes things a little bit more complicated, because now we have a longer trend, and then at some point maybe humans jumped into this trend and started hunting and disrupting food webs or whatever. But disentangle this process is important, because if we really need to restore from a reference point, we need to know where this reference point is. So if we think everything was caused by humans, we just need to go back to when humans didn't have these capabilities of hunting so effectively, and then we just can have that as a reference point for restoration. But if we acknowledge that this is a longer term process, driven, of course, I didn't mention, but these trends would have been driven by environmental changes, specifically the spread of C4 grasslands in Africa that we know from isotopic data sets and other proxies. So the idea is that this is caused by this change of vegetation cover. Also, in the same context, we have the bovids radiating in like hugely. It's amazing, the radiation of bovids. So there must be some component of competition maybe, or just relocation of biomass somehow to these smaller body size categories. And of course, maybe at some point, the human effect. So if this is the case, the problem is where do you go, to what point in the past we can go back to have like a reference point for restoration, right? So I'm going to focus on this scenario in these tests. So we have the pattern. So we have an emptying of a local diversity of herbivores, and we have a relocation of biomass and abundance in different size categories. But we don't know how this happened, because if we want to look at this regionally, this is like, so diversity is like a bank account. So you can decrease your money by spending more, that would be extinction, or because your salary just drops, which is speciation drops. This is the two ways you can decrease the number of species of megaherbivores in a system. But nobody looked at it yet, because people assume everything was extinction, and they're just trying to do different tests of extinction with different correlates. So we are going to look at speciation and extinction rates, per capita rates, which is really what gives us the process thing. So what's behind these things. Second thing is we want to really see if there is an extinction selectivity driven by body sizes. So if larger things are really going faster to disappearance, if they are going extinct at a faster pace, or if there is more parts of the phenotype, like for example dentition, which is a proxy for dietary plasticity, that could be also like modulating this response to the environmental change as was proposed by these other authors. So maybe this is a more complex scenario that just larger things go extinct faster, well, for whatever the reason. And then the third part is checking the tempo. So these studies have proposed that the spread of grassland and the increase in aridity are responsible for this decline. So we want to check for if the tempo of this decline is actually in accordance with the tempo of increasing aridity in Africa. I will explain to you now how we get this. So in order to test these issues or these problematics, we gathered data for African ungulates for the last 24 million years. This is around 400 species, more or less. And this made up a total of about 3,000 data points or records, right? For every species, we have size in terms of 6 categories, and we have ipsodonty in 3 categories, okay? So this is low crown teeth, kind of a little bit high crown teeth, and very high crown teeth. And these are supposed to be able to deal with harsher material, so you can eat more things like, if you think about elephants, even wood and things like this, because even if you're grinding like really wearing materials, your teeth still endure longer enough, right? So there's supposed to be a more flexible diet also associated with this. So you can graze more, and if you have this dentition, you're more, in principle, more restricted to things like fruits and leaves and sprouts and things like this. And then we have this environmental proxy, which is aridity. And we get this from sea cores near the eastern coast of Africa, and this is like kind of like the reference now for this environmental change. So this is like the position of dust or dust flux in these sea cores across all these interval that we are studying. So we will use this curve, which is the lowest curve, to fit to the model, to check what's the role of aridity in all this. So now, okay, we have all the data, and we just need one model now to analyze this data. So of course, analysis of speciation and extinction are not new. We can learn how these two rates change over time. We have been doing this since the 50s, more or less. So there's nothing new in this. But then we want to change how these rates change across different body size categories and across different levels of ipsodonty. And of course, all the possible combinations between these two traits. But also, of course, we need to introduce aridity in the model to see if aridity is affecting in the same way different sizes and different dentitions. And also, just in case these two traits, size and ipsodonty, is not good enough, we can implement phylogeny to control for how these effects propagate through different lineages, but also maybe there is signals like lifestyle traits or behavior, social behavior, or who knows what, that we are not capturing with body size and dentition, but we can capture definitely by including the phylogeny. Okay, and this all sounds wonderful, and it would be even better that given a rate and a factor, each of whatever size category could have like completely different shapes of correlation. We don't need to stick to linear correlations because these things can be really complicated. And all this is amazing, but we were not able to do this until this year because this takes like a lot of flexibility in the model. But thank God that I was able to collaborate with two really smart persons from the Fribourg University, and we developed a version of Pirate, which is a software for diversification analysis that is able to account for all this complexity, all these factors, all this non-linear relation, all the interactions between all these things, etc., etc. So now for the first time, we can really put all these variables in the same analysis, rank them in importance, and look at their effects across lineages, okay? Okay, so jumping into results, the first thing we can look at, because now the cool thing about this system is we will have all these amazingly huge vomit of data, and then like looking into that is like the really hard work. So the analysis is not so complicated. What is really complicated here is to reconstruct what happened in this neural network system. So this is like rates through time, so you can see blue is going to be speciation across the whole talk, and then red is going to be extinction. So you can see that the whole system, so all African ungulates, are like starting to lose, so negative net diversification when extinction goes above speciation, right? We start losing species. So the whole system has been losing species for the last million years or so, more or less, right? But of course, this is just for everybody, so we are not looking at any correlation here. This is just the classic, what the classic results would look like, but we really now can look what it's under this blanket, no? Like what's really happening here. So just for, we can start looking at the best predictors of speciation here and extinction. So for speciation, body mass is the best variable to explain changes in speciation, but also phylogeny and aridity, and in a not so important place, ipsodonty. And for extinction, what we have is that aridity is the major, but by far, the major variable here. Also, there is a very important interaction between these two, aridity and dentition, ipsodonty, and then body mass, not so important, phylogeny, not so important. So this means that the effect was really widespread across phylogeny, this extinction peak we saw in the beginning. So let's look at body size, because we're talking about the extinction of megaherbivores. So the good thing about this model is I can give you just the effect of body size. This is not like rates across body size categories. This is the effect of body size after excluding the rest. So doesn't matter what's the phylogenetic position, the dentition, the aridity, the whatever, no? Just body size. And it's funny because what we see is that they have the bigger ungulates, they have lower speciation and lower extinction than other categories, right? So you can see here everything above 1,000 kilos, which is 2 different categories. So this is this contrast with what I had read in many papers saying that larger things overall, they just have a higher risk of extinction, right? So it seems like thanks to this model, we are able now to tear apart what factors really drove these things to extinction. Because if larger things, they have a lower extinction risk, then how can we explain a biased decline of megaherbivores in the system, right? So now is when we are going to take advantage of this new model and start tearing apart all these effects. So as I said, aridity increase across this time interval is very important, and we can isolate this effect also. So you can see here, this is the whole effect, only the effect of aridity. So aridity is the x-axis, and this is rate, so red is extinction again. Aridity alone is responsible for a 20-fold increase in extinction across the whole interval. This is a huge extinction peak across every lineage, every ecology, everything. Whereas it's changing a little bit of speciation alone. The higher, so speciation in the higher level of speciation driven by aridity is only like a 30% increase. You know? Now this is interesting because then we can say, okay, there's a point where we have, for example, maximum speciation and minimum extinction driven by aridity. So there's an intermediate point where the whole system, the effect of aridity is really positive for diversity. Species are multiplying faster. And this is around 6 million years. So this is in the beginning of the expansion of the C4 grasses. And we have species really multiplying very fast, and aridity has somehow depressed extinction. And then we have a moment which is where aridity predicts a net decrease of diversity. This is where extinction surpasses speciation. And this happens around 2.1 million years. So this is a moment where just the effect of aridity, so again, this is not all the rates, possible rates, just the effect of aridity, is predicting that the whole system should, if aridity would be the only controller here, driving the African ungulate diversity downwards. But now the cool thing is we can start looking at interactions. So we can say, okay, so what's the effect of aridity across body sizes and in terms of speciation and extinction? And this is where the interesting things start to appear. So as we increase aridity, what we see is that the larger categories, which are here, the darker lines, they drop completely their speciation potential. They are not able to produce a species that fast. And what we see is that larger things are only producing species at a fourth of the rate as smaller stuff. So this is a huge, huge difference in the for this process. Whereas if you look at extinction, more or less everybody is going up as we increase aridity. But interestingly, the darker lines, which are the larger, the megaherbivores, are going extinct at a slower pace of the smaller stuff. So it's not even extinction pushed up by aridity what is driving the larger things to their disappearance. The major difference is here, is speciation, okay? And this is going to be very interesting because this is a bank account where basically my monthly expenses are kind of similar compared to others, but I'm making less money each month. So this is how I emptied my bank account. We can also look at the effect in ipsodonty, which is not very important for extinction, sorry, for speciation, but there is some interesting, important interaction between ipsodonty and aridity. So we see that even like this trait is also saying, showing some differences here. So ipsodont stuff, so things that can eat everything from grass to boot to whatever, to browse, they have only 60% of the extinction rate, the things that are more restricted to, like we could say, forested habitat or the food that you can find in more forested habitats. So these two things are going to start shaping the whole process. And I'm going to start unfolding a little bit more what we have found. So we can isolate everything below 1,000 kilos for different ipsodonty levels and look at the timing of the red line going above the blue line. And we can do the same for everything above 1,000 kilos. And you can see, for example, that among these 6 plots, those that start losing species faster are the brachydont large things, so the browsers, basically, things like a dinothere and things like some mammutis or gomphotheres, things like this. They start disappearing around 3 million years, more or less. So this is more like telling us what happened, what was reported in these papers I was mentioning in the beginning. Like 3 million years, we start to empty parts of the ecospace very, very early. Whereas things which are big bar ipsodont, they start losing species later on, okay? And then, of course, we have some interesting things here, which is the speciation potential we were seeing before in small things. So you can see here in this upper right plot, this is the bovid radiation. Most of the bovids are there. From these 170 species, 140 are bovids, okay? You can see the levels of the blue curve here compared to levels of the blue curve in the other plots. This is like huge. So basically, this is also how we see this relocation of biomass starting to be put in the shape of a bovid more and more often, right? Because this is happening at the same time that productivity is dropping with aridity. So it's like we have decrease in productivity overall, and then we have this lineage that is multiplying as crazy, okay? So this is a way to look at the data, at the results, at the correlations, but also we can come back to the essentials of our 6 body mass categories, and then our 3 ipsodont categories, and then we can build this simple ecospace, call it whatever you want, where we have all these different 18 possibilities in our ecological data set. And then we can just say, okay, what's the rate? What's the predicted rate for each of these combinations across different timings? So I'm showing here the last 7 million years, speciation, extinction, net diversification. So basically, what is very interesting is that larger browsers, so everything in this part, they have really low speciation potential. This is the lowest speciation potential we have. And this is getting worse and worse because there is a point where we don't even have more species there, right? Because they go extinct. So even though you can have some green parts here, so this is net diversification, it's important that you look at what is going on. Because you can start losing species like here or here without very super high extinction, just because your speciation potential is also very, very low, okay? And even though we have some really dark or fast speciation rates, remember this is per capita rate. And in fact, for example, if you look at this very red square here, this is just the extinction of one species, which is the last dinothere that disappeared in Africa. Okay, so it's not that a red dot here means like 20 species disappear suddenly. It could be just one species, the last one of its categories, the only thing that was here. So basically, this allows us to start looking at what is really going on through time, through ecologies, et cetera, et cetera. But as I said, bear in mind that everything above 1,000 kilos, so the upper 3 rows, they're really in pale blue. And this is going to be very important for us to be able to empty the megaherbivore niche, which is everything above this dashed line here, even if we don't increase extinction very much, okay? But of course, we are ignoring phylogeny here, so this is everybody put together, like rhinos, anthracotheres, dinotheres, whatever. But the good thing is we have phylogeny, so we can take that to just bring one lineage. So if we can, for example, take elephantids here, and then you can see how the speciation potential is here driven by ipsodonty. So ipsodont forms in the rightmost column is allowing these lineages to multiply faster, okay? Whereas extinction seems to be starting from the browsing part of the ecospace, okay? So we have here, I mean, we can talk about also species selection and things like this. But of course, you can see here in the lineage was basically in green for a long time. So this is a big elephantid radiation in Africa. And only in the last 700,000, 800,000 years, the whole lineage started to be in red. Okay, so this is really, really recent, much recent than the dinosaurs, for example. So there is a difference in timing regarding your diet, not just your size. So the megaherbivores decline is much more complex than just being large or not. And of course, if we do this for one family, we can do this for all the families that we have. Okay, so this is how much we can unfold all the results from this model. And this is the flexibility of this model. And this is what takes really super long to process. Because now here you can see, well, we were looking at the elephantids, now we can look at the dinosaur, which is funny because even if you have a single species for most of these last 7 million years, we can see how its extinction risk is increasing over time, because extinction risk is function of aridity, and aridity is increasing across these different time intervals. And it's a brachydon, and it's above 5,000 kilos. So we know that we are predicting the extinction risk over time, even before the species go extinct, which happens definitely in this last red square over there. Okay, and we can do the same for every single species. You can see the mammutids, which is another family, and the gomphothids, which is another proboscidean family. They all go extinct really, really earlier than the rest of the proboscideans, the elephantids. Okay, so there is like this dietary signal in this process. So this agrees with the idea that this long-term decline in the megaherbivore niche was mainly driven by changes in vegetation cover and how these different lineages could cope with this or not. So we have horses here, same thing. But they are already the Ipsodon horses, what we see in Africa, so they last long, and they are still around, of course. You can see that they only get into negative diversification very late in the sequence. Calicotheres, not very diverse. Rhinos, also like not showing super high extinction, but they also have this very low speciation potential compared to other lineages. So this is why many of these were also lost in this moment, because the speciation was really low. We have the wild boars here, speciating as crazy, very, very blue colors here, but also having really high extinction. These are probably the guys with the higher extinction rates across the whole panel. So their turnover, what we call the turnover, was really, really fast. And you can see here how this translates into net diversification. So complete, like entire parts of the eco space, they were being lost also. We have hippos. Here in hippos, we see a change. So here, for example, speciation was more between being a brachydont or ipsodont, but in hippos is driven by body size. And we see this change. So larger things seems to be just driven by diet, but as we go towards like the smaller stuff and the artiodactyls, we see that the gradient is size related instead of diet related, right? So it's a very complex, system, no? It's very, and it's the first time we can really look at this, put numbers into this, and understand really what's going on. The same for, you can see also here extinction. So for hippos, this idea holds that smaller things were going extinct faster than larger things, okay? So you can see how the gradient decreased upwards. So again, larger things, they don't have inherent higher risk of extinction. These are anthracotheres, they are not doing much. I think it's just one species by this time. We have giraffids and relatives, so giraffoids. Here, same thing, browsers rotating here, but then they never evolved really super high dentitions, so they are like a little bit doomed with this change of aridity. And finally, the big radiation of bovids here. So they had this sustained, very positive, very green diversification rate for a long time. So they were just taking all the resources, all the biomass. This is what explains this shift, this relocation of biomass from the larger stuff to the smaller body size categories is mainly driven, I think, by the radiation of bovids, because they are able to suppress, unlike the wild boars that start to going extinct very fast, around 2 million years, bovids are able to suppress extinction like a lot. So, and that's because these are logarithmic process, like just by depressing extinction, even if your speciation stays constant, you can just gain in diversity very fast. So you can see how these colors are really, really pale in general. So these guys were really multiplying very fast in net numbers. So with this, I'm going to just go through a few conclusions, and then we can discuss or go back to some slide if you're interested. So basically, for the first time, we are tackling the decline of megaherbivores, not just looking at extinctions and its potential correlate, but also speciation. We have found that we can only explain really what happened if we take into account this change in aridity or the spread of C4 grasslands, which are really tightly related over time in the model. But interestingly, we found that the correlates of body size with extinction and speciation is not what we hoped to find. So we really see that the bigger factor here is that larger things, they have a really low speciation potential. So it's not all about extinction, but probably the more important factor in these disparate changes in diversity across the ecospace is basically speciation potential and not extinction. This is where we really find the difference. This could be, there could be some learning here even for how we deal with the current biotic crisis, of course. But not only body mass or just aridity, but we really need to look at other aspects of ecology, and maybe in future versions of this model, we can even input more traits and still be able to get much more information. But also it was important that we were able to input the phylogeny, so every trait that was family related, because this phylogeny is at the level of the families that we have been talking about. All these traits that we have not coded implicitly here, but are somehow reflected by phylogeny, were taken into account. And finally, if we really want to think about what reference or baseline we need to have for megaherbivores communities to be able to restore these processes and these species in current ecosystem, then what we found is making things much more complex than if we just thought everything was an amazing world dominated by giants and humans arrived and they killed them all and that was it. Now we see that there is much more complexity around this subject, and that I think this makes decisions a little bit less clear for picking up a restoration baseline. So with this, I just want to thank you again for attending the seminar, and I hope you enjoyed it. Tienes que hablar por el micro.
Pasamos ahora a preguntas que tengáis, dudas sobre lo que se ha mencionado aquí.
Thanks for the talk, very nice and colorful. I was wondering if you could use your model or apply your model to the predators and the carnivores and so on to see whether extinction or speciation rates mirror extinction or speciation rates in other members of the fauna in these habitats?
Yeah, so potentially this model, you can include the whole African large mammal data set, so including carnivores, and then analyze them. Maybe you can do a dietary trait and then just distinguish between carnivores, herbivores, or different types of carnivory or herbivory, and then see, because for every trait you know all these interactions, so probably you can even look at correlates. That's a way to do it. So, but for example, some of the co-authors that I mentioned are working on a global ungulate database, and they are looking at carnivore interaction in the shape of the number of species of carnivores coexisting with each species of herbivore over time. So somehow a proxy for carnivore pressure or something, which is, I mean, you cannot go down to abundance of each species because we don't have that detail in the paleo record. But of course you can come up with proxies that make sense. Or you can even think of just diversity of carnivores over time, and instead of adding the species themselves, you can just add another environmental curve. So you could put aridity, and then in the side you can do African, so the diversity of African carnivores, for example, and see how this affects the whole thing. Yeah, it's very flexible. That's the good thing. You can add more traits, you can add more environmental variables, whatever you can think of, and you can actually even make, because here, for example, aridity is affecting everybody in the same way. So aridity at some point is the same for all the species. But if you can come up or think about a variable that changes over time or in different places, so if you have a curve for different continents, so and that curve changes, you can actually do like tables for each time being where everything changes if you want, and it's different for a species depending on the continent, so you can really put a lot of complexity into these models. Of course, the higher the complexity, the higher the data set you need to back up that model. But yeah, you can do a lot of things now.
Thank you, Juan. It was a great talk. I have some questions. Can you do this, the same analysis, can you repeat them using time windows? So can you check for predictors at different times? So maybe they change over time?
Yeah.
Do you know what I mean?
Yeah, actually, I didn't mention that. So, or I show it, but I didn't mention, but let me go back to the model. So here, when I said that we can build the model and then make it change through time, also time is a variable here.
Okay.
Yeah, I forgot to mention that because it's very important. So this means that when you have aridity being so important, it means it's so good at predicting changes in extinction that relegates time itself as a potential variable to a third or fourth position. So this is like an insurance that really aridity is capturing so this is an important comment that you made, because so this is not just we allow like aridity as the only time changing variable. No, we have time itself as a variable, and then we add aridity on top of it, and then aridity is relegating time to the last position at explaining variance. So this means that aridity is a really good predictor for the patterns we see.
And related to time, all the graphs that you showed, are those calculated in relative time or absolute time? Because they are from 0 to 1, so I didn't understand this very well.
You mean in the...
in the last slides? They were
so
from
these
0
are,
to 1.
Yeah, so these are time beams.
Because I think they went from 1 to, sorry, like 3 or 4 backward. That you saw the aridity factor. Affecting both rates.
Yeah, the aridity factor is on centimeters deposited per year or something like this.
But these graphs, you saw a time between 0 and 1. Is this relative? Is calculated in relative time, or is?
No, this is going from. Oh, sorry, I'm not sharing my screen anymore.
Just a curiosity.
Yeah. So this goes through time.
Not that one.
Not this one.
No, I think it was when you saw the aridity affecting extinction.
Okay, yeah.
And the other predictor size. There were a couple of graphs with
Here.
yeah, exactly. That
Yeah, because now time, so this is time, but now here in the y-axis, we have rate.
Yeah.
So now this axis become the x-axis. So this axis, which is like grams per square centimeter per 1,000 years, this graph now is horizontal here. And this graph goes between 0 and 2, more or less. But now the lowest line goes only until 1.12 or something like that. So this is why now what I'm showing here is just the span of the lowest curve, because it's the thing we feed into the model.
And last question, I'm sorry.
That's fine.
At the beginning of the presentation, you said, if I understood correctly, that your data set consists of communities per site. Is that correct?
Well, the data is records which are presence of species in localities, yeah.
And you have several species per locality, for instance. Do you
Yeah.
have this data?
Yeah.
Have you tested for community assembly processes? Now
Not-
there are
not in-
approaches. Now there are approaches that you can even test for different processes or predictors of community assembly over time, and it's very cool. You can or test which kind of processes are accounting for the community at that time.
Mm-hmm.
If it's dispersal or environmental filtering, or now I don't remember the third one, competition. These three processes. So there are also approaches that you can test. Maybe you can use this data for another approach,
like,
more community ecology.
Yeah,
study.
so if you, so all these two papers I showed, these are locality based. So all these points are localities. I wanted to have like a regional process because I really wanted to look at the speciation, and you can only do that at a larger. But of course, yeah, we have done many, for the Iberian Peninsula, for example, we have done community paleoecology stuff.
Oh, nice.
And of course, you can, like including food webs or things like this, or functional structure. And of course, you can then, that would be cool. But I think that part, like this team led by Tyler Fate, is like more into that, just looking at more at the process within communities. So we'll leave it to them for now.
Thank you so much. It was great.
Thank you.
Thank you very much for the talk. It was really very interesting that aridity was the main factor related to extinction risk. And as someone not well educated with paleoecology or paleobiology, my relatively naive question is there any way that aridity may also affect the quality of paleodata?
It could. I mean, open savannas are supposed to be better at preserving. So one thing that you only need to be very careful when you run this type of analysis is to take sampling biases into account. And for this model, what we are doing is controlling for sampling across time. So each time being is not only allowed to have different speciation and extinction rates, but also different sampling rates. Because if you don't do that, for example, if you go from a timing where you have just a few fossil localities and then you have a bin which has like 1,000 fossil localities and you don't control for that, then what you will have is many species appear suddenly in the second bin, right? So that would give you like a spike in speciation. So one thing we control is this time changing sampling to control for that. But also this model allows you to allow a change of sampling across different species. Because you can have some species that even if this bin is really well sampled, the species has just one occurrence. And the model is able to look at that. So, okay, this is a species which has only one occurrence, but it is in a really well sampled bin. So that's going to be differently treated that if that's a species with a single record, for example, is in a badly sampled bin, where everybody is really badly sampled, for example. And so Thorsten Haufe, who is the person that led the development of this model, is now working on another version where everything you saw across like phylogeny and aridity, so all the changes in speciation and extinction rate that we saw, you will be able to also allow sampling to change in the same way. But of course, to do that, you will need databases that are like really, really big. But if that's something that end up working, and I think it will be very interesting because, for example, one can have some suspicion, maybe not for the African record, but for others, where smaller things are not sampled as often. We don't find them as often as very large stuff. So you could say, okay, I'm going to allow sampling to change across body size categories, for example. So you would add that layer of complexity on top of the just sampling changing across time and across different species. But that's still, I think, in preparation. So, but it would be cool to have, yeah.
Thank you.
Yeah.
Thank you for the talk. I really enjoyed it. I have a question related to what Rafa asked, and this thing about different trophic levels. And you said that you could add, for example, the carnivore pressure. But I wonder more if you, I don't know if you already tested some of this or not, but if you have an intuition whether the effect of body size could be delayed somehow across trophic levels on time. Like if carnivores, for example, would also be, like larger carnivores would also be more affected or have less speciation, but in a different time period, like later on as a response.
Yeah, so this is something I haven't tested, but I have this belief that what we saw here, so larger things becoming less abundant, this is something that the upper trophic level is going to mimic, basically. So we will have, because larger things, they have this problem that they need to cover larger ranges to find the same amount of food, but everything else being the same, no? And we see that as this productivity drops, what happens is larger things are not able to speciate so often, and that's in part why these things are going empty so fast. And I think this will happen exactly the same, because at the end, you have less productivity going into the herbivores trophic level. You will have smaller herbivores overall, and then this will happen again in the top level. So I think this is a process that starts with changes in vegetation, the spread of grasslands with C4 grasses, which are not necessarily the same in nutrition. So I think that they are usually less quality. If you are able to eat grass is great because you have grass all over the place. But those animals like some proboscideans that only feed on fruits and stuff like that, they need to travel like maybe longer, or they just cannot sustain their populations. And I think this is exactly what could happen to carnivores, so that the same process just goes up to the next level, and then you will have a relocation of carnivore biomass towards smaller sizes.
So you think it would happen more or less at the same time? Like
Yeah.
the delay, it's more in ecological time scales, not that you wouldn't see a difference at this super large.
Yeah, I think at least for some species that maybe were like super large and specialized in hunting really big herbivores, if now most of the herbivores are around 100 kilos, from between 50 kilos to 200 or 300 kilos, then you may have like more mid-sized carnivore species more specialized in this. For example, this is a guess, but it would be cool to do this same thing we did for herbivores, for carnivores, to try to bring the relative abundance and relative biomass for carnivores too.
Yeah, thank you.
Thank you very much for your talk. I wonder if there is any influence of what we can call the phylogenetic inertia, that is the pattern of phylogenetic change in the different groups you have considered in the results. Because if I understood well, everything seems to be related, the pattern of extinction and speciation, to the ecological of the climatic change. And my question is if you have considered what could be the influence of this phylogenetic inertia in the different groups you are considering?
Yeah, so one cool thing about how phylogeny is input here is that it's not just, we are not labeling species in a family and then we just have a discrete character saying Deinotheres, bovids, whatever. We really input the distances, the phylogenetic distances of the tree in the system. So this is a way to control for that signal. And I think there is actually, since phylogeny is input in this way, because phylogeny is always one of the top main factors explaining both speciation and extinction, it's very, very evident that there is a phylogenetic signal. So there is something that is not captured only by body mass or by ipsodonty, but by being part of a lineage. So the family you belong to is going to dictate a lot of what happened to all these species. No? So yeah, absolutely, yeah.
Any further question? I just have a small one. Curiosity more than any other thing. The different groups that you consider, they have very different social life. And then there are many that are in an enormous number of specimens and others that are more scattered or even isolated in some areas of, not in Africa, well, some of the African too. So is that, I imagine that also interfere or is a factor to be considered in the real sites, I mean, from a taphonomic part. So is...
Yeah. So, for example, I think, well, there are things like how, for example, you can gather in herds. So some animals here, they probably are more solitary, like rhinos. You have things that move in herds, like elephantids. We don't know how Deinotheres were gathering socially, but probably they were not forming really big herds. They were probably more like small groups in dense forests, because this is a very old lineage. And they are probably not having anything to do with the elephantid way of organizing in societies. So that, of course, is at the same time dictated by size, and if you have to migrate a lot to find food, because if you think about elephants, for example, they migrate all together, but they cover huge areas, because there is this paper where they say the very large herbivores, they are tricking the system because they are not feeding in the same trophic pyramid, but they move across a lot of seasonally changing trophic pyramids. So they can do that because they go in herds, they have this mating system, etc. And of course, that's going to be a really big part. It's like for bovids, you have these really compact herds of sort of antelopes, and this is related because they are grazers and because they are in open habitats, so it's also related with anti-predatory strategies, so everything is like super connected. And of course, I think it makes the difference, because if you feed on trees or forested habitats that start to shrink, and you don't have this migratory behavior like elephants do have today, then you are stuck where you are. You can move maybe inside your patch of food, but maybe you cannot just do like elephants going through deserts and savannas, because they can just eat everything. So this also, of course, is going to have an impact on the extinction rate and the speciation rate.
Thank you. Well, if there are no more questions, thank you very much all to come here, and thank you very much, Juan, to come to give this talk.
Thank you.